So good morning, everyone. I hope you really enjoyed the company yesterday at the reception and are now ready for the first day of the scientific program. So now we can start into the science, we can start into the Spark sessions, and it's my pleasure to introduce the person who is moderating the Spark session, Tom Crawford. So he's a well-known person at the HLF, so he was our morning show news host at the digital HLF and has been returning as a journalist and as a moderator several times. So Tom is a mathematician at the University of Oxford and University of Cambridge who is very interested in outreach for mathematics, has his own channel, Tom Rocks Math, and has an impressive over 30 million views on YouTube. So Tom, the floor is yours.
Thank you. Always an absolute pleasure to be invited back to Heidelberg every year. And I'm going to start with a message for the young researchers, which I think I've said a few times now, but bears repeating as most of you will be new this year. You can think of it as there are two ways to make it onto this stage. You can either become a laureate in your subject and spend a lifetime doing fantastic, novel, groundbreaking research. Or in my case, you can record yourself taking high school maths exams and put them on the internet. So I'll leave it to you to decide which of those you would prefer to do. So I will be your host pretty much every morning this week, so no lie-ins for me. The idea behind the name of Spark Talk is these are meant to be short and sweet to kind of spark inspiration and further discussion throughout the week, and it means we get to hear from lots of different people. So hopefully you will enjoy the format as much as I do. So on that note, our first speaker is Sanjeev Arora, and this is very relevant to what I mentioned about taking videos that I make of me taking maths exams, because I've been trying to do one from various different countries around the world. And on most of my videos, there is a comment saying that I should take the JEE exam from India because it's the hardest in the world. This is what the comments tell me. And our first, I've yet to try it, but our first speaker, Sanjeev, so Sanjeev actually was ranked #1 in this exam in 1986. So Sanjeev has done both. He has done exams and become a laureate. He was awarded the 2011 ACM Prize in Computing, and today we'll be speaking on, will there be a superhuman AI mathematician? So Sanjeev, thank you.
It's a pleasure to kick off the event on AI, and I'll be talking about a superhuman AI mathematician, and I just want to start slow, first talk. Everybody here knows what's happening in AI, and we started with these things, language models, which basically are trained on a lot of text to predict the next word. So given this sentence, Rob went to the cafe and ordered a blank, it'll come up with completions, namely a probability assigned to all these plausible words, latte, Danish, tea, etc. And using that, it'll produce the next word, and then it can continue and produce more and more words by this kind of prediction process. So this is what language models were until 2 or 3 years ago. They were derisively even called stochastic parrots. Now, starting 23, things changed, and they became much more complicated and interesting. These days, they are trained on general purpose skills, not just text. So programming, math, science, understanding images, audio, you name it. And the training is not just this training on next word prediction, the probabilities of next word, but a complicated multi-stage training. And also, these have become commercial products, so many details are not revealed anymore, but you hear about it over a beer or something. And data is generated lately in the current generation of models by AI itself. So it's not that they are just parroting back things they saw on the internet. A large part of the training data these days is believed to have been actually generated by AI. And the word is that it's actually better than human data in some ways. And finally, there's this idea of self-improvement where the AI improves itself, and I'll give you some simple examples of that. And yeah, there are pioneers here among the laureates who've worked on this and made it happen over the years. And you'll be hearing from them. All right, so therefore this stochastic parrots view is not valid anymore, I think. And so now, going on to the AI super mathematician, it's important to understand this background, which is very relevant to this joint math and CS audience. From the early part of the 20th century, the dream of automating math. So it goes back actually much further. There were scientists already in the 17th century thinking about automating calculations, which was what mathematicians did back then, and had some interesting ideas, which were even implemented. But it really kicked off when David Hilbert, the world's most famous mathematician at the time, suggested that maybe mathematics could be completely formalized and made mechanical. And soon after, Russell and Whitehead came up with this framework, Principia Mathematica, which was a logical framework where everything could be derived in a mechanical way, and which also was the inspiration for the modern computers. So that was a dream of automated math, but the dream was quickly shattered by these famous discoveries, such as the Gödel incompleteness theorem, that you could have an axiomatic framework, but it would be incomplete or unsound in some way. And related to that was the work of Church and Turing, where they essentially invented computers in an intellectual sense and showed that if you think of this proving as a computation, then it can't always halt. It cannot always decide correctness of all math statements. So I'm guessing you've seen some of that in your undergrad preparation. And then there was NP completeness, and there are even some of the laureates who sometimes attend who discovered it, which showed also some kind of a complexity barrier, that it gets very hard to find proofs. So yes, it's mechanical, but it may take super polynomial time. So in that sense, limitations are shown on how good automated math can get. And today, the most relevant thing out of that line of work will be the idea of formal verification. So the fact that math proofs can be written in a way so that they can be rigorously checked using logic. And this is an important idea in computer science today as well. And that P versus NP inside says that logical proofs can be checked. Even if it's hard to come up with them, come up with the proofs, it's easy to check. And in the setting of math, there's this framework called Lean, very cool graphic, existential and for all quantifiers, which is a programming language. And whenever you write a proof in English, there is in principle a way to translate it into this programming language. And the back end of this programming language is this compiler and proof assistant, which using that programmatic description of the proof can try to prove it. And when it succeeds, then you know the theorem is correct. And so you start with a proof, you rewrite in Lean format. This is currently done by humans, but very soon will be done by AI. And you write it in Lean, and then it can be verified by this checker, and thumbs up, thumbs down, and you know whether it's correct. Okay, by the way, last week, Morph Labs, an AI startup, announced a radically faster converter, but it hasn't been released yet. Okay, so now with this background, we are ready to discuss what is the meaning of a superhuman AI mathematician. So imagine conceptually the set of all possible math theorems, what these famous minds were thinking about. And these are the ones proven by humans at any time. And superhuman AI mathematician means that this AI model is able to prove theorems over time after you run it for a long time that are strictly more than the set of theorems that humans have proven. And furthermore, it would be verified in something like lean. So even if it's a long proof, we humans can trust that it's correct. All right. So again, where we are giving up compared to these pioneers 100 years ago is that we don't expect this to be perfect. It just has to be better than humans. Okay? And then you get away from undecidability and all that. Okay, so how do you get there? And currently, of course, there'll be speakers today who might argue that AI is going to go even much, much further than math, and probably they're right. But for math, at least the path seems already pretty clear, and within the next 5, 10 years, you expect to see a lot of progress. Okay, so in background, you should understand what is this. I referred to this earlier, the self-improvement process. What is that? It's something called reinforcement learning, although it's a more advanced form of reinforcement learning than the old days. And there are some pioneers of reinforcement learning who will be speaking here. So this is that end stage of training the AI that I mentioned, and it's actually, these days, considered the most important stage. And just simplifying a whole lot, the idea is that you give the AI, which has already been trained a lot, a large question bank created by humans. And so feed it questions one at a time. And it's already trained so it can generate answers. So it's allowed many attempts, so you collect many solutions. And now, from there, you use the correct ones for training. And how do you get the correct ones? So that's the human feedback. Some human has labeled them with the correct answers. And then, so that's the thumbs up, thumbs down. So that's a famous pipeline at this point. But in the case of math, building on everything that happened in the 20th century, you can automate that to some extent. So remember, there were these humans who were deciding whether the answer is correct. But in math, you can verify the answers with lean if they're written appropriately. So if you just ask AI to produce its proofs in lean, it can be automatically checked. So now you replace the human graders with lean, and now this becomes much more efficient. It's not bottlenecked by humans, and so this can really take off, and that's what's been done. And so that's a big source of progress, automation. There's something else going on right now in math pipelines that they're actually not training on very hard math, but when you go to proof-based math, that's what you need. But now, here's the key new idea, which seems plausible. So you got rid of the checkers, the human checkers. Do you still need the humans to generate the questions? And there's increasing evidence that actually the AI itself can generate very good questions. So therefore, you won't need the large question bank from humans. I mean, it would train on human data somewhat, but then it takes off. And a copy of the learner itself, the one who's learning to be a mathematician, would produce the questions. Now that sounds crazy when you first hear it, but why can this work? Well, remember, I mean, everybody here has interacted with the AI a little bit. And the strong suit, or maybe the strongest suit of AI is the creativity. That it trains on this massive amount of data, and then it can find things across this data set and combine them in interesting ways. So that kind of creativity. So it has trained already on the math books and so on, math papers. And so it knows the definitions and the concepts, and then you hope that it can be creative at producing new questions. Now, of course, it's creative, but it can hallucinate, right? It doesn't have a very good idea of truth. But you have lean verification for math. So, if it produces a question, tries to come up with an answer, if the answer isn't lean, you can verify it. Okay, so it prevents that from going off track. And this is not just a theoretical idea. This has been done at some scale, not clearly at superhuman scale, and it works. In alpha geometry, this Google DeepMind project, basically the prover took no human data and was completely bootstrapped. But in some of the other settings, it has been trained on human data, and then it's bootstrapped. Gödel Prover is a new project that our team at Princeton released, and unlike some of the other provers, we actually completely revealed our methodology and our code and data. So yes, you can check it. That it really did improve from its self-generated questions. So sorry, there's some formatting issue. Yeah. So other notable recent news I mentioned already: our Gödel Prover project from Princeton. So DeepSeek, the AI startup in China, had released this prover, which was the best open prover. And our 8 billion and 32 billion models are much smaller, but they beat it handily. They are secret, as in like unreleased models from OpenAI and Google, which achieves the IMO gold level performance, as you read in the newspaper. It won me a nice lunch from a colleague who I had a bet with about this. And then these teams, after OpenAI and Google announced that, there were these open efforts, UCLA team first, and we verified that at Princeton too, that you can use these current open models that we all have access to. You have to pay for it, and using 10 to 20 rounds of self-correction. So it solves a question, then asks it to itself to correct it. Another copy of itself to correct it, to grade it, and then generate, grade, etc. And after 10, 20 rounds, basically they can solve 5 questions, which is gold level. And recently, as I mentioned, there's this AI startup which is devoted to formal proofs, and they announced this major improvement in AI translation from English to Lean. So Terry Tao and Alex Kontorovich, famous mathematicians, have been trying to convert this major theorem on prime numbers into Lean, and they thought it would take a couple years of human effort, and it was done in 4 weeks. So yeah, things are happening, as you know, in AI very fast. So to conclude, that's the picture we're talking about, superhuman AI. And I think that's fairly likely to happen. And math is the likely first domain because of verified answers. So this whole pipeline really takes off if there's verified answers. And I also mentioned that it will take AI to produce its own questions, and that also seems feasible. And the superhuman performance arises from this self-improvement process. And this has been shown to work at some scale, and it's conjectured that it can go all the way. And yeah, just remember that this math superintelligence does not mean it's perfect, just that it's better than humans. And the reason it can get better than humans is because it's basically tireless. And it can just keep repeating, and do this self-improvement loop and get better. So that's the magic, if you want to call it. OK, I'll stop there. Thank you very much. I'll take questions.
So we are out of time for questions, I'm afraid, Sanjeev. But of course, I'm sure you would be happy to answer anything in the coffee break and throughout your rest of the time here. So just can we thank Sanjeev once again. Thank you. OK. Now, I've had the pleasure of introducing our second speaker this morning quite a few times. But only yesterday did I learn of this fantastic story of him as a high school student having access to a computer in the engineering lab at UCLA and going in on weekends to work with this computer. And one particular Saturday, the lab was locked. And being the person that he is, decided that would not stop him from accessing the computer on a Saturday. And so he spotted a second-floor window which was open, and then proceeded to climb on the shoulders of his good friend, Steve Crocker, who I believe might actually be here, to then open and climb through the second-floor window and then open the door. And then did you tape the door so you could still get back in and out? So I think that shows commitment to the cause right there. So as I said, my great pleasure to introduce our second speaker, Vint Cerf, who was awarded the 2004 ACM Turing Award, and today will be speaking on digital vellum. Vint.
I can't quite tell. Is Steve Crocker actually in the room? I don't see him standing up anywhere or waving his hands. But he is a man upon whose shoulders I have been standing since 1961. And it's important for you to appreciate it was 1961 when we were getting access to a computer. That's nothing new for most of you who are a little younger than we are, but back then that was hard to do. Okay, so I will probably use up all of my time, and so you'll have to catch me at another time to do questions. I just want to pose the problem, and then we'll talk about why this is a hard problem to solve. Content has been stored away in various forms for many, many years, thousands of years. Look at the cuneiform on clay tablets, for example. You wouldn't think clay is a very long-lasting storage medium, but often these were warehouse records, and the warehouses burned down and baked the clay, and so the clay lasted for 6,000 years. If you could still read cuneiform, and there are probably a few people in the world who still can. And if you look at the history of storing content, information, you'll find that it gets shorter and shorter time frames for a lot of the technology. So the next thing is Vellum, which is calf skin or goat skin. Sometimes those manuscripts last 2,000 years. And then there's rag content paper, which lasts for at least 500 years. We have good examples of that. And so there are all these media, and they have one thing in common. They don't require any electricity in order to be read and preserved. But now we get to the digital era, and digital content is stored in media that does not have a particularly long life. Some of these you'll recognize, and very few of them have any facilities for readers anymore. The little 3.5-inch floppy disks, I found some in my basement office a few years ago, and I wondered what was on them. And I didn't have a 3.5-inch floppy reader, so I found one on eBay, and I plugged it into my computer and discovered that there were WordPerfect files on this 3.5-inch floppy disk, but I didn't have a WordPerfect program that I could run until I found an old computer. It was an IBM ThinkPad that had an old WordPerfect running on it. And so I was able to copy that and then write it into Microsoft Word of 1997. And then I had a Macintosh that knew how to run Word 97 and translate it into 2004. So the point here is that these media do not have a natural longevity. And it gets worse, because what about the kinds of static material like video or imagery and things like that? You do need software in order to correctly interpret these formats. But it gets worse than that. What about executable content? Now, all of a sudden, it's not just static material that has to be correctly translated and rendered, but now you have to have an execution environment in order to experience some of these kinds of digital content. So executable content is a really hard thing to achieve, because you have to recreate an environment in which the software can run. And when you think a little bit about the context in which you have to recreate, it's a non-trivial exercise. Some of you, I'm sure, are familiar with the Internet Archive, which has been running for over 30 years now. They're about to announce they have 1 trillion web pages stored away in the Internet Archive. But in order to do that, they have to take in the web pages, and then they have to translate the URLs into something that can be resolved within the context of the Internet Archive, not within the context of the entire World Wide Web. So there are all kinds of transformations that are needed in order to achieve these objectives. So if you think a little bit about the problems you have to solve, they're not just technical. I mean, it's clear that we have to know how to interpret the bits that are stored away. What is the format of the bits? What do they mean? You may need to have some metadata to even explain why do I have these bits and why do I want to keep them, or what are they? Where did they come from? What is the provenance? What kinds of software is needed to correctly render the bits or interpret the bits? Do I have the source code or the executable code of the software that's needed to interpret the bits? And in what environment do I have to run that application? Well, that means you may have to have access to an operating system that knows how to run that particular executable application program. So now you have to go and get the operating system to go with it to run the application that knows how to interpret the bits. But now the operating system has to run on some kind of a computer. But what if that computer doesn't exist anymore? So now you have to go figure out what the instruction set is of the computer that the operating system ran on, recreate that environment in order to run that operating system, et cetera, et cetera. Well, this is going to take up a lot of bits to recreate these environments, and so you'll have to have room for lots and lots of digital content to create these environments. Then you run into another little problem. It's intellectual property. Sometimes people like to claim they own the operating system or they own the application program. And sometimes when companies go bankrupt, at least in the US, the bankruptcy proceedings treat that intellectual property as having value. And so they don't just give it away for free or make it available publicly. They often try to sell it to somebody in order to recover some of the bankruptcy losses. So you have run into interference trying to get access to operating systems or access to application programs so that you can correctly interpret these bits. Now, I want you to be thinking about this in terms of hundreds of years, not 10 years or 20 years. And so you can imagine it's 2125, and someone wants to know what went on at the Heidelberg Laureate Forum in 2025. Are there any examples of the software that was used to make presentations? Recreating an environment 100 years later is not going to be a trivial matter. So, and because we have fights over intellectual property, we may even need to have changes in the laws in order to deal with access to content that you would need in order to recreate these environments. So you can imagine copyright laws and other intellectual patent laws having to be modified to give at least the archivists the authority to have copies of these things that they can use. So I'm not going to be able to go through all the slides that I have, but I want you to appreciate the scope of work that's required to preserve digital things and the problems that we will have to solve. The scope of the environment that has to be regenerated is significant. And so what I would like very much to talk to you about when we have a chance on the boat or in any other settings is what kinds of solutions you might be able to come up with for properly recreating these environments so that digital content can be preserved over time. I have some more slides, but I'm going to stop there and give back my time to the rest of the speakers, and I look forward to talking to you about the solutions to some of these problems. Thanks very much.
Hey, thank you very much, Vint. All right, so our third speaker of the morning. So as you may have realized, I have been attempting to find interesting stories about all of our speakers. And for our third speaker, I discovered he used to take part in national school Scrabble competitions, which I didn't know existed until today, which is brilliant. And there is a story that he discussed in an interview a couple of years ago, where he made it to the final game of the championship. And sort of towards the end of the game, his opponent played a particular word to which he couldn't help but respond and say, "Are you sure you want to play that one? There's a much better word, which is this." And then his opponent, of course, obliged, and I believe won the championship off the back of such advice, which I think gives a really interesting insight into his approach to games and competitive things of that nature. So our third speaker is David Silver. He was awarded the 2019 ACM Prize in Computing, and this morning he will talk on the theme of Era of Experience. David.
Thank you. Feels like a long time since those days of playing Scrabble, but I will talk about something which I think touches on some of those themes of what it means to understand and do something really well, maybe for the pleasure of it, maybe to learn from it. And this takes us to the era of experience. So I think we would all agree that the current era of AI has been dominated by learning from human data. Systems which are basically trained from massive scale data on the internet, primarily natural language, but also other forms of human data, which are then fine-tuned from human feedback. This is preferences, examples, and other human data that then gets fed in. And this has led to enormous progress. We've seen LLMs, large language models with wide-ranging knowledge that can do vastly complex activities, unprecedented performance on tasks from law to math to software. But I think it's also true that this kind of AI can't, in isolation, deliver superintelligence. It can't discover new knowledge, new paradigms, new ways of thinking that go beyond the things that humans know. And I think this behooves us to really think about what paradigm for AI will take us there, what will take us all the way to something which is superintelligent. I think furthermore, it is also fair to say, and maybe this is a personal perspective, but I think if you provide the knowledge that humans already have into the AI, it doesn't really answer the deepest scientific question for AI, which is how a system, an AI, can actually learn for itself to solve problems. We've provided it with human answers and human knowledge and the human way of doing things, and then it's able to, from that, distill and figure out, and that's amazing, but I think there's a deeper question, which is how a system can learn for itself. So, if you could play this video, please. We'll see an example of something which is learning in a really different way. This is a baby sped up many times, which is in this stream of experience. It's just exploring its playroom. It's touching many things. It's got this intrinsic motivation to kind of just figure out what each of these different objects does and messes around with them, tries fiddling with them. Over there, it goes to some little, the door. I don't even know the word for it, the boingy thing that attaches to a door, and just plays around with it for a while. It's just fascinated by this kind of sensory motor experience that it inhabits, and it's learning about it. It's like figuring out how things work. And it's using that experience to develop, over time, profound knowledge about the way that the world around us actually works. And I think that provides a different perspective to how a system might learn. It might learn from this experience of this stream of observations and actions that it takes in this world. Can we go to the next slide, please? Okay, so I think once we understand that experience provides these additional benefits, I think there will be an inevitable transition. This is something which at some point must happen en route to AI systems that actually are able to go beyond human levels of intelligence. This must happen at some point. And I think some of this transition to the era of experience has already started. And by this, I mean agents that, they really will learn from experience. They will learn from, and by experience, I mean, an agent that interacts with its environment, and the data of that interaction as it itself goes through this stream of experience. It's that data of its actions and observations and what happens as it does these things that it will learn from. This will be done at vast scales. And I think the scales at which this happens will eventually vastly exceed the scale of the internet. The internet seems so huge to us, all the things that humans have discovered over time, that at some point in the future, that knowledge will seem small, and the knowledge that agents learn for themselves will be far larger than that. And this will be transformative. So I think there's a potential here to transform AI through the continual discovery of new knowledge and new capabilities. And that is a path that feels like it will lead to superhuman forms of intelligence. Okay, so now let's dig into this a little bit more and ask, what might the characteristics be of this era of experience? And I think, we can capture these characteristics by, thinking about that baby in the video. And I think our agents in the era of experience will also have some of those characteristics, like the baby. And this doesn't have to be, a physically embedded, like an animal-like intelligence. It could be something which is doing, science. It could be something which is embedded in trading applications. It could be a language-based AI. But I think these 4 characteristics will apply in all cases. Agents will inhabit streams of experience, long lifetimes of interacting, taking actions, and observing what happens. And these actions and observations will be richly grounded in the environment. They won't just be like, a human talking to a language model and getting the response. The agent will be able to do things in its environment, act upon the world, and get rich observations back from the world. And the rewards, the goals that the agent seeks to optimize, these will also be grounded in experience. They'll come from the world. It will try to optimize for outcomes that actually occur in the world, and not just things which, maybe, as we saw previously, where humans say, that action was good or that action was bad. The rewards will be grounded in what actually happens in the world. And finally, the agents will plan and/or reason about experience. And I think these characteristics do not exist in the kind of typical approach that large language models take today, although change is starting, and we've seen that some of these elements are starting to find their way in, which suggests that this transition is perhaps on its way. Now, we could say, weren't we here a few years ago? These thoughts which I'm trying to utter to you now are not new. They've been around for a long time. And there have been successful examples of systems that learn for themselves through interacting with their environment. Some of them we did ourselves, and others from other labs have been very successful too. Examples like Atari and AlphaGo and AlphaZero brought a lot of excitement to this idea that systems could learn for themselves, at least in simulated environments. And so we might call this the era of simulation. But the advent of large language models kind of transformed the way that people think about AI, took attention away from that, delivering some amazing progress. But I think it kind of threw out the baby with the bathwater in some sense, and I think it's time to transition back, and that will inevitably transition back to the era of experience. We're starting to see, AIs that interact through computer control, through other ways to interact with the world, through controlling terminals and GUIs and things like this, the ability to at least manipulate their digital environment. This is happening, and it's a sign that change is coming now. But I think it's still true that if you really look at the field today, there's this one lamppost that has been casting a very bright light onto the ground, and most of the AI field has been kind of searching for solutions under the light that's been cast by this first lamp, the era of human data. And relatively little attention has been applied to this other lamp that is maybe currently further in the distance somewhere, but which perhaps offers the potential to really change the paradigm. So what happened? Why did this change occur? Well, I think it happened for very understandable reasons, that human data provided a shortcut. We found, you can think of the human data that's on the internet as like a fossil fuel that we discovered in the ground. Like all this knowledge was already there. And we could, our AI systems were able to kind of consume this knowledge, and that provided enormous generality. Like this knowledge, it covered a vast range of things. And it was far cheaper to consume that knowledge than to actually go and interact with the world. And so for those reasons, we built systems that built upon that knowledge and have actually used up most of those fossil fuels at this point. Maybe I think there's more that can be done. The fuels can be burnt more efficiently, if you like. But in some sense, this was solving the shallow problem of AI. When the knowledge is already there, how do we build systems that kind of can distill that knowledge into something that we can use? But there's a deeper problem of AI, which is how to learn, a system can learn for itself. Experience is required to go beyond. And you can think of this experience as like a renewable energy, like taking this analogy further, an energy that can keep going forever. It's something which, if we get this right, systems will just be able to learn and learn and keep learning and accumulating knowledge and trying things out and improving and trying them out and getting better. And the world will provide the generality. Like, the world is vastly complex. It contains a huge range of signals that we can optimize. And, like the baby, it was messing around with all these different things just in that one playroom environment. There was so much to do. The world will provide the generality. There are so many signals to optimize that, we will be able to find that generality. But we have to pay the cost of interaction to do this. Okay. I want to talk briefly about some success stories of reinforcement learning, which is, if you like, the science of learning from experience. And you could think of these as steps towards the era of experience, none of which in themselves, represents the complete picture, but each of which kind of captures, like a microcosm of what it's like to succeed in this way. And we've seen, success stories in board games, things like chess and Go, video games, Atari, StarCraft, and so forth, robotics, manipulation, locomotion, mathematics, which has already been mentioned, achieving ACM A.M medal, discovering better ways to, solve problems like matrix multiplication and so forth. Okay, so briefly, I'm going to talk about, three, if I get to at least two case studies that I was involved in and enjoyed working on. So the first is AlphaZero. Going back a few years. And this was a really simple algorithm that started from basically random weights in a neural network and was able to train itself through self-play, basically have a program play games against itself millions of times and improve and improve and improve until it reached very strong performance in various different domains. And the algorithm is like surprisingly simple. Step one is it performs a tree search using the policy that it has so far, which starts as random, and the value function to evaluate positions and see how well it's doing. And that's the planning step. The second is that it updates the policy towards the best action that it found during search. That's the policy improvement step. And the third thing is it updates its value function, its way to evaluate towards the outcome of these self-play games. And that's the policy evaluation step. And when you repeat these three steps, many times, something amazing happens, which is you have a system which, when it's placed down into one of many different domains, and each of those separate domains is able to start from essentially no knowledge of that domain and actually reach superhuman performance, like discover things that no human knew and achieve levels of performance in those games that no human was able to achieve. And this was true in chess, in shogi, and in Go, in all of those cases. The second case study, and thanks to Sanjeev for doing the background to this, is AlphaProof. So this is something we did last year, and this was the first system with the help of alpha geometry to achieve a medal in the International Mathematics Olympiad. And it basically applied exactly the same approach that we just saw on the last slide to formal mathematics. Basically treating formal mathematics, if you like, as a game, a single-player game, and solving the game with this very straightforward AlphaZero algorithm. And so what this shows here is, at the top we see the actions that you can take in this game, which are things that you can write. It's like basically it's a system that's writing lean code and executing that code and getting a reward based on whether it was got the correct proof or not. And so the actions it takes are like adding in a new tactic, like there's a new tactic here, like this min-fact function is being added at the top there. And then there's a neural network which basically learns which tactics to take and also what value those are likely to give, how much they contribute to the likelihood of getting the proof correct. And then we can do tree search in this space, the same Monte Carlo tree search we used before for AlphaZero. And then you apply the same ideas, and lo and behold, the system was able to achieve the top silver medal in the system and was actually able to solve the hardest problem in the 2024 International Mathematics Olympiad that was solved by less than 1% of humans. And the solution that it found is shown here. It's a non-trivial proof that was discovered by this system that started, in this case, not from random weights, but from a very weak prior, where it was fed a kind of weak prior about how to code, basically, things like this. So the last case study I want to show is, oh, by the way, this alpha proof is finally going to be published in the next couple of weeks, so you can read more about that in, I think that's going to come out in Nature in a couple of weeks. This third case study, very briefly, is about how to discover algorithms. How can a system actually figure out good algorithms for itself? And the problem that we want to address here is that RL, reinforcement learning, is actually really hard. It's got these non-differentiable objectives, unlike supervised learning. The best recipe appears to vary quite a lot between environments. And to date, there are no general-purpose, robust algorithms. And I think this is one of the reasons why the era of experience hasn't yet fully taken off or achieved the limits of what could be done. But perhaps there's a path out of this, which we could, by applying the same idea at the meta level. So the idea here, this is work we did in 2022, but again is actually just about to be published, is to actually learn how to learn from experience. So it's like doing the same idea at the meta level. So if you like, the idea here is to have an agent that interacts with many environments, and it basically is trying out different learning algorithms represented by a neural network. And it just keeps trying those out and trying them out and seeing how well they do. And based on how much a reward it accumulates in each of those algorithms accumulates, it adjusts the neural network that represents the learning rule, and it's able to learn a better and better learning rule over time. So this system really discovers the learning rule and goes on to actually outperform the best reinforcement learning algorithms that any human has discovered on the main reinforcement learning benchmarks that people have used over the last decade. OK, so call to arms then for all the young researchers in this room, which is, the potential is there, the methods we've started to see, some of the ideas are out there, but really the challenge is out there to solve the deep problem of AI, how to learn from experience. Like the baby in the video, like how can we build a system that is as incredible at really just extracting knowledge from the things it does in its environment. And this will be a profound moment for science, actually, I think, if we solve this deep problem. And if we do this, it will transform the future of AI and thereby humanity. Thank you.
OK, which brings us to our penultimate speaker, Madhu Sudan. Now, when I was looking up interesting stories and facts about Madhu, I discovered that he had the same doctoral advisor as our first speaker, Sanjeev Arora, which makes them academic brothers, according to the Math Genealogy Project. And also, on the list of students of their PhD supervisor, Umesh Vazirani at UC Berkeley, there is at least one other laureate on that list. There may be more, which I think is incredibly impressive as a PhD supervisor to have at least 3 laureates there. Madhu was awarded the 2002 Abacus Medal, as it's now known, and today we'll be talking on quality control in sublinear time. So, Madhu.
So for a little bit of a change in pace, I'll be telling you about some recent work that we've been doing. I'm a theoretical computer scientist. I try to build mathematical models of what are some challenges from computing and try to give you some analysis and some theorems related to that which might guide us in the future. Now, for the field of theory of computer science, this is a very transformational moment because up until now, all of computer science, which had its origins in logic, as Sanjeev reminded us earlier, has always worried about correctness of algorithms. You come up with a specification of what you want to do. You design an algorithm and you try to make sure it's correct for the task that you want to solve. And then you try to optimize this algorithm for the worst possible case and input case. This has some very positive features. Performance is guaranteed on every input. And we can start building a rich collection of reductions. You can have an algorithm A calling an algorithm B, calling another algorithm C. And there is a whole network of algorithms that are working on top of each other, and they're all correct and successful because every algorithm is supposed to be correct on every input. Unfortunately, this is also very pessimistic and slow. In particular, you have barriers like the uncomputability barrier, which says some functions cannot be computed by algorithms at all, and the intractability barrier like P versus NP, which says some things which may be solvable will not be solvable fast enough. So we do have challenges imposed by this, and the world has moved on beyond these challenges. In practice, what we end up seeing is not a focus on this worst-case input, but rather try to design data-driven algorithms. You look at the distribution of data that comes along, try to understand what it represents, capture it, and then move along. And you always optimize for the current benchmark set. Now, this begs the question, how do you model correctness in this setting? What is safety? But let's talk about the positive aspects. We learn things very quickly. We then learn to predict very quickly based on this. So these are very, very fast. In fact, you can even come up with models of how these algorithms work, which are based on if an input comes from a certain distribution, then this algorithm is going to be actually fast, and I can prove this analytically. Unfortunately, there's this challenge. Is this distribution the correct one, modeling the real world? And even more specifically, if this is an algorithm that is going to determine whether or not you as a person get a mortgage that you're seeking or are found eligible for parole, is this input correct on my data? Is my data really from this distribution? So there is a big challenge, which is the gap between trying to design an algorithm which works in general and an algorithm on this particular input. Should I trust its answer today or not? So this is the question that we decided to model theoretically. And we went along and said, OK, here are a few things that we can hope to do. So there's two challenges that every theoretician faces in these kinds of challenges. First, there's a definitional challenge. How do I model the question that we want to solve? And then there's a plausibility challenge. I can come up with fantastic sounding definitions which say this is what I want to achieve, and then come up with a theorem which says none of these definitions are satisfiable. So there's a plausibility challenge. We want to say there is some hope that this is going to work. So we have to set the right correctness criteria and then prove that the definition is viable and ideally take it to practice. I'm not going to go all the way there. This is really our first work in its first year. We're going to see a definition and then a viability proof. I won't give you the proof. I'll give you a claim that if you believe will be a proof. And then there's a question of, is this going to be useful in practice? And I'm hoping you're all going to be able to engage in that question and answer. Our hope and our inspiration for this new definition comes from what you see commonly in the area I'm calling quality control. This is what is alluded to in the title of my talk. So consider a person who's looking at a product line and is looking at every output product and saying, is this a good enough product to be sent to the shops, to the consumers, or should I hold it back on accounts of some flaws? What are their mandates? Well, ideally, I'm not claiming any particular store does this exactly this way, but this is, I think, the theory behind it. A bad product should not be allowed to get through. Simply no rotten tomatoes in the output. It's okay to reject a few good products every once in a while because you're not sure and you'd rather be safe than sorry. But you should not be rejecting everything, saying, oh, this could be bad, this could be bad, this could be bad. And you also don't want to be taking forever per product. There's some very valuable lessons over here that help us design some definitions, and this is what we use to define quality control. We intend to apply it to, say, a learning algorithm that you may have, or any other algorithm which is trying to look at some input X, tries to compute some value associated with it. We'll define the value by some function called rho. X is, and we want to compute V is rho of X. We want to know, did we really manage to do this? So we put in a quality control at the end of this thing, which looks at X and this value computed by this algorithm and says, is this really the right one? Should I trust this algorithm on this particular input or not? And the way we decided to model take the lessons from quality control and apply it over here is given in these two equations. I will amplify what we are saying in these equations on the next slide. So what we've decided to do over here is look at two notions that have always been associated with correctness of algorithms, correctness of proofs, which is completeness and their soundness, and put an asymmetric expectation from the two. Completeness usually says, on the products that I should let through, am I letting them through? Here we are going to make this an average case guarantee. Most products that are good will be let through. We don't say all products that are going to be good will be let through. So this means on an algorithm, when an algorithm runs on a particular input, sometimes we might say, no, I'm not sure. But actually, the algorithm was fine, but we might just say, I'm not sure. That's OK. And this is captured by putting this probabilistic expectation around the algorithm's correctness. On the other hand, when it comes to soundness, we said no matter which input you're considering, we should always have, if the algorithm's output is not correct, it's not close to being correct, we should absolutely say no, and this should be said with very high probability, and we should be able to boost this probability as much as we like. This is the math which captures it. I will not parse the equations very carefully, but trust me, if you understand these kinds of statements and you've seen them before, this will make complete sense to you. If not, please come talk to me about it. So this is modeling almost everything about quality control except one aspect, which is we wanted this whole process to run in very, very fast. We did not get that yet. And we will add that to this thing by defining something called, reminding you of something called sublinear time algorithms. But before I do that, let me just quickly say these definitions that I came up with did not come up in a vacuum. There's been a long history of work in average case completeness due to Levin in the 80s. There's work on how do you refute a particular statement, how do you prove that some graph is not three-colorable, and Feiger's work on refutation contributed to some of the ideas in our definition, and also Rubenfeld and Vasilian, who had some very recent progress on what does it mean to be able to test or not, trust or not trust a distributional assumption. So all of these went into our definition, so just some credits over there. Sublinear time, finally, how do we define very fast algorithms? These are algorithms that need to run much faster than even time taken to scan all of the input. We don't have time to read everything. We'll be scanning, sampling some things, and coming up with the data. This is very plausible, and it's been used as a model since the 1990s and has led to amazing results in our field. In our case, we will be giving random access to this input to our quality control algorithm and asking it to do well. Okay, so this leads to this is the solution to our definitional challenge. Now let me tell you a little bit about the plausibility. What were we able to do? We took a very, very simple problem. I'm given some large graph. It's coming up from some random network where every edge is independently in or not in with probability p. This is the famous Erdős-Renyi model of random graphs, GNP. And in this graph, I want to count the number of k cliques approximately. Let's say k is 5. I want to know how many subsets of 5 vertices are completely connected with each other. Can you count this very fast? Now, if you look at standard results, this will actually prove to you that this is going to take a lot of time. The lot of time is given by some parameter which has k squared in the exponent. And what we were able to do is prove that actually you can get reduce this exponent to k by using the axioms of quality control. Okay? Why this problem? It's a very, very basic graph theory problem. For graphs, counting number of occurrences of subgraphs is like looking at the moments of some n-variate real distribution. So this is amongst the most fundamental questions we could think about, and we were able to analyze it. The tools that we were able to use over here involve a beautiful mix of probability, combinatorics, quasi-randomness, and if any of these words make any sense to you, please come talk to me about it, and I can tell you much more about it. And one wonderful aspect of this result that I want to highlight is this definition of quality control is just perfectly suited for composition. You can just compose algorithms randomly, put them together. When I'm given an input and I want to test it for a particular parameter, and I want to say, is this aspect of this input good? I can reject it for any other reason that I want to reject that's completely consistent with our definitions. It's going to satisfy everything, and this makes it very easy to design algorithms in this space. That's all I wanted to say today. Thank you very much.
Naturally, there will be nobody who wants to ask a question. Yes, okay, that was a very excitable hand. In like, maybe wave again. Yeah, we've got a magic box that's going to be thrown at you.
Ooh, somebody else. All right.
It will be a standard question. You just jump over it. You said there is a key insight, and you said 2 words about it. Can you develop a bit more?
Sure. I mean, I can just tell you one elaboration of that sentence. What's the key insight? I have an input, and I want to say, did I compute the number of cliques of size 5 correctly? And I might reject. I'll try to count the number of cliques of size 3 in this graph and say, look, is this number roughly like it should be in this random graph model? If this number is not right, we reject it. This is definitely one of the sort of key insights behind our thing. We are rejecting it for the wrong reason, but that's completely allowed by our model of correctness. Thank you.
And the final round of applause there for Madhu as well. Thank you. Okay, which brings us on to our final speaker of the morning, and surprisingly on time. Very well done, everybody. Richard Sutton will be our final speaker. And continuing the theme of academic families, Richard is the PhD supervisor, or was the PhD supervisor, of our third speaker, David Silver. Richard was awarded the 2024 ACM Turing Award, and today we'll talk on the future of artificial intelligence. Richard.
Good morning, everybody. My topic today, the future of artificial intelligence, it's kind of way too big to hope to do thoroughly, but I hope to say some comments around the edges and make some progress. Within your lifetime, AI researchers will understand the principles of intelligence well enough to create or become beings of far greater intelligence than current humans. Amazing to say it. Yeah. It'll probably take decades, and if you want to think of it as a race, then it's not a sprint. It's more like a marathon. It will be the greatest intellectual achievement of all time. I really think of it as a grand prize for science, engineering, and the humanities, all of these three. We've always tried to understand ourselves. The significance beyond humanity, really, beyond life, beyond good and bad, it's a big deal. We are incredibly ambitious. Also, I feel that this step will just be an unalloyed good. It'll just be a good thing. I mean, of course, this is the future. The future is what it is. There'll be good things and bad things that happen. But I don't think the bad things will be due to an excess of intelligence. And finally, full superintelligence, I think, will require learning from experience, just like David talked about. Yeah, I'll take all that as read. So, if this is going to be happening in the next decade or two, and you want to be ambitious in your research and contribute to this grand prize, I think the main thing is not to be distracted by incidental things that don't really lead to this. So I have a long list here. Don't be distracted by applications. Don't be distracted by domain knowledge. Don't be distracted by large language models. I think they're not on the path. Don't be distracted by mathematical things like optimality, regret, variations thereof. Don't be distracted by unnecessary variations in the problem, multi-agents, risk sensitivity, multi-objectives, all these things. They're not really on the key path, in my opinion. It's only my opinion. That's what I can have to offer. Also, don't be distracted by concerns about safety or explainability, privacy, most things that people will work on. Don't be distracted by new environments or simulators. Instead, we should be focusing on designing better learning algorithms, better planning algorithms. And I have a whole paper with my colleagues on this. You might want to check out the Alberta Plan for AI Research on arXiv. Okay, so that was my first of the three main messages that I'm going to try to communicate today. I think AI is coming, and if you want to be part of it, don't get distracted. Keep your eyes on the prize of understanding intelligence. And perhaps understanding intelligence as a way of interacting and learning and thinking about experience. So let's now, my second and third points are actually on politics and on philosophy. So on politics, I want to say first that AI's politics today is politically charged, sort of a focus of geopolitical competition between nation states, and the public is fearful that AI will lead to bad things, and we need to control it and pass laws or pause it. Many, many calls and great fear. I'm happy we don't really see too much fear here. Here we seem to just revel in intellectual progress and just the beauty of understanding. I like that attitude. That's what I'd like to be promoting today. So I'd like to ask this question. In a society of multiple agents, and that's really what a society is there only one goal, or are there many goals, just like there are many agents? If you look at reinforcement learning, each agent will have its own goal because it has its own reward, its own pains and pleasures. Just as in nature, each animal has its own pains and pleasures. And I think this is the way it works for people too in our economies. Our economies work best when different people have different goals and different people have different abilities. They really don't rely on people having a shared common goal. They more use collaboration and our markets. So basically, agents can coexist in peace, even when they all want different things. Maybe this is obvious, but I think it deserves to be restated in today's world when there are many calls to control the goals of artificial intelligent agents. So we can want different things, it's okay. We can still coexist, work together, live in peace. So I want to make a couple definitions to talk about this. One is decentralization. Decentralization is basically this view of many agents, each pursuing their own goal. And cooperation is when such agents with different goals interact to further each their own goal, mutual benefit. Okay, so I think this cooperation is in fact humanity's superpower. It's what distinguishes us from other animals. Humans cooperate much more than any other animal. Cooperation is facilitated by language and money, both unique human inventions. Our greatest successes are cooperations, our economies, our markets, our governments. And our greatest failures are our failures to cooperate, like war and theft and corruption. The view of decentralized cooperation is an alternative to what is in some sense the normal nominal philosophy of our society, is that we have a common purpose that we're working towards. Now, I think we all have many different purposes, and it's good that it works that way. In my view, it's more elegant and sustainable to have this notion of decentralized cooperation towards different goals. So humans are better at cooperation than any other animal, but we're still terrible at it. We still do have wars. We still do have corruption and theft and fraud. Basically, we struggle to cooperate. And of course, cooperation is not always possible. It takes multiple trustworthy agents, and there are some that are going to benefit from not cooperating. We have cheats and thieves and weapons manufacturers and dictators. Cooperation needs institutions, maybe centralized institutions, in order to facilitate it and to punish the cheaters and the fraudsters. So these centralized authorities, they can help cooperation in the short term, but there's the danger that they will poison it in the long run when our governments or our centralized authorities become authoritarian and sclerotic. So the message, I think, is that we have this spectrum or these two perspectives, and centralized control is really the opposite of decentralized cooperation. And this tension we see throughout our politics, and it's the central tension of our time. In particular, if we look at what's going on today, there are many calls for centralized control of AI, just as there are many calls for centralized control of people. We're trying to control AI, we allow which goals they would be allowed, we might want to pause or stop research, we might want to limit the computer power of AIs, or there are many calls to ensure that AIs are safe and disclosed. So this is very similar, I think eerily similar, to the calls for centralized control of people, for controlling what people can say and what people can hear, for controlling the trade between people and where they can work, and how they can control their finances, where can they take their money out of a country, economic sanctions and tariffs. So these arguments for centralized control of AI and people are eerily similar. They're all based on fear. You have to fear the other country, the other people, or the AIs, because they're different than us. They're all about us versus them. They're all demonizing the other. They all claim the other, the AI, or the other people can't be trusted. So, just to conclude on politics, human and AI perhaps flourishing comes from decentralized cooperation. Humans are great at cooperation, but also terrible at it, and it's not always possible, but it's the source really of all that is good in the world, and so we must look for it and seek to institutionalize it. And if we look with open eyes, it's easy to see who is calling for mistrust, non-cooperation, and centralized control. We should resist those calls, and that this is a useful lens with which to view all calls for human and AI interaction. Okay, so I think I have a few minutes for my last message about the philosophy of AI. So AI is happening today and ever more so tomorrow. What are we to feel about it? Is it good? Is it bad? Is it something we'll lament AI's rise, or will we celebrate it as related to our own? Is it us or is it not us? So basically, perhaps you have a sense of my opinion, my feeling about it. And I feel that AI is not some alien technology. It's really one of the oldest of human strivings. For thousands of years, philosophers and ordinary people have sought to understand their intelligence. People have always been fascinated by how they work and wanted their minds to work better. This is a grand quest. And to understand intelligence, I think, is the holy grail. It's a great and glorious scientific prize, intellectual prize. Okay, but let's just be realistic for a moment and just say what's going to happen. Set aside what we want to happen or don't want to happen. What will happen? And I offer 4 tenets of realistic AI prediction. First tenet is there's no consensus about how the world should be run. No one view is dominant over the sum of all the others. The American empire is not strong enough to control the whole world. The Chinese empire or country is not strong enough to dominate over the sum of all the others. Number 2, someday people will understand intelligence well enough to create it with technology, and they will do it. We won't stop there. Soon, the intelligence of current humans will be vastly exceeded. And point number 4, over time, it's inevitable that power and resources will flow to the most intelligent. So given those 4 tenets, I think we end up with the idea that that maybe like this. There's the ascent of humanity, the succession to AI is inevitable. But even this point of view is rather self-centered for humans. Like, it's still human-centric. What's happening to us? But can we get a different perspective? What would just the universe say about all this? It may be grandiose, but I like to think of it a little bit in grandiose terms. So I would distinguish 4 great ages of the universe. The age of, after the Big Bang, the particles, and the second age, the age of stars. They collapsed into stars and formed, and they exploded, made heavier elements. Eventually they formed planets. And on the planets, we get the third age, where we have the age, you might want to think the age of life, but I would like to say the age of replicators, where there's lots of things that can self-replicate. And so the third age, these replicated things are most prominent, and that we are in the midst of the transition to the 4th great age. And the 4th great age is the age of design, where most things are designed, are created first in the minds of some replicator, and then created in reality. Most things are designed. We look about us today, almost everything is designed. You know, your chairs are designed, your clothes are designed, the buildings are designed, but the people are replicated. People are replicators. So, yeah, it's tempting to talk about the age of life and the age of machines. I think it's the real difference between biology and technology is that there's a difference between replication and design. Design things, of course, are more easily improved. And many non-human replicators, animals, are designers. They make nests and burrows, and crows do this, chimpanzees do this. Humans make stone axes and spaceships, software and tools for making other tools. So the final slide is, what are humans? Maybe we can answer this question. What are humans? What's our role in the universe? Can we answer this dispassionately without hubris? Because we all sense that people are special, that we're not just another replicator, but in what way are we special? In what extent? Well, we are the replicator that's taken design to vastly greater heights. Can we think about taking it all the way? What would it mean to take design to its limit? I think it really means to design things that are themselves capable of designing. And this is what we're doing with AI. And thus, humans are at least the catalyst or the midwife or the progenitor that fulfills the age of design, the 4th great age of the universe. And that completes my 3 main messages, the last one being that AI is the inevitable next step in the development of the universe, and we should embrace it with courage, pride, and a sense of adventure. Thank you very much.
Right, so that's the end. So if we could just say a final thank you to all 5 of our speakers, so Sanjeev Arora, Vint Cerf, David Silver, Madhu Sudan, and Richard Sutton. We just do a final round of applause for all 5 fantastic talks we've had this morning. So that's the end. So if we could just say a final thank you to all 5 of our speakers, so Sanjeev Arora, Vint Cerf, David Silver, Madhu Sudan, and Richard Sutton. We just do a final round of applause for all 5 fantastic talks we've had this morning.